So, welcome to this week's Origins Colloquium. It's held jointly with the Kavli Summer Program in Astrophysics, organized by Shazreen Mohammed at University of Virginia this summer. And it's a great pleasure to welcome Andrew Udin to give the talk. So, Andrew received his PhD from UC Berkeley in 2003. He was advised by Frank Xu and was working then on many aspects of planet formation, including, of course, the very famous streaming instability, which he then later developed and published when he was a postdoc at Princeton. And after that, he was at CETA and Harvard for postdoc positions before joining University of Arizona as a faculty member, where he is today. So he's worked on a wide range of topics in planet formation, and we'll hear today about formation of giant planets. So welcome, Andrew.
All right. Thanks, John. Obviously it's been great being here as part of the program, and it's now great to interact with some others. Obviously, giant planet formation. We're getting a bit away from the small dust that's been the focus of this workshop, but this is, of course, where most of the dust in the solar system wound up. At least the planetary component winds up in the giant planets. So I'll be trying to tell this story that's developed over the years about how giant planets form. My understanding is that this is supposed to be a very interactive seminar, roughly evenly split between me talking and you talking. So I'd like to not leave all of that to the end. So please interrupt me as we go. If there's something you want to hear more about, something you disagree with, have something to add to, any of that is all good. Please don't hesitate. So I guess I'll see if my slides advance. Oh, there we go. Oh, I tried to skip my fun slide. Okay, here we go. This is unfortunately my last week here. There are a couple of very important things I need to get back to. Apparently, I don't know what was going on last night at home. Well, I think this is like a Mardi Gras necklace. The older belonged to the older sister, so she's already being a bad influence on on the little one. So I need to get back and try and take care of that. One of the reasons I'm talking about giant planet formation, it's something I've been somewhat actively working on, and people in our group in Arizona have been working on. But I also recently went through the exercise of writing a review chapter with Xiaowan, and of course it's really great to work with Xiaowan because he's very thorough. He's an amazing theorist and simulator who's also very tightly connected to the observations, and so it really got me thinking about this sort of holistically in a way I had not done before. And so that was great. I want to try and share that and discuss that with you. Just, I don't know if we've obviously got some people in the workshop who are not, don't work on planets so much. So what is a giant planet? Well, our idea of giant planets obviously came from our solar system, where we broadly think of there being two classes of giant planets, these sort of gas giants, where the vast majority of their mass is in hydrogen and helium. And then there's the ice giants, where actually most of the mass is in a rocky, icy core, but they do have a gaseous envelope that includes hydrogen as well. And so then when we went on to, and the field went on to discover so many extrasolar planets, we sort of course, took these ideas from the solar system and then mapped them on to what we found. And so if we found things that were kind of like Jupiter, but, close in because they're transiting, we call them hot Jupiters. And if we find things that are in between these objects or below these objects, or between the ice giants and the terrestrial planets, we sort of give them names relative to what we're familiar with in the solar system: sub-Neptunes, super-Earths, all of that good stuff. What's actually going on inside these objects? Is there a pointer here? I guess it wouldn't really work for the online crowd. So
We can see your cursor, so if you want to just move that.
yeah, well, I have to hunch over and need a lectern in here. But yeah, I think that people online can see as well. These are sort of standard ways in planetary science, scientists who study the interior here. You can then see the point I was trying to make, that these ice giants, the hydrogen helium component is really a relatively small component of their overall budget, even though you still call them giant planets of a sort. And then just a little terminology of what we think are parts of giant planets. When we talk about the atmosphere, people generally just refer to the thin part, including the photosphere that we can actually observe directly. But one of the characteristics of most giant planets is they have a much deeper envelope of gas that the terrestrial planets usually don't. And then another feature that seems to be common in or at least we think is common in many giant planets, is the existence of heavy elements, not hydrogen and helium, that have at least partially condensed out into a core. Although a lot of recent work is suggesting that this heavy element core may not be completely segregated from the hydrogen and helium, and there may be mixing of the heavy elements with the gas element. And that comes from detailed solar system observations of Jupiter and Saturn. Now this is where I might expect some discussion. How do we decide whether something is a big giant planet or a tiny star, right? A lot of debate goes into this. One of the most common things that is said is, well, stars, we think of them as things that undergo nucleosynthesis of some sort. And even though brown dwarfs don't have a lot of nucleosynthesis, right, objects which are above roughly 13 Jupiter masses do have a brief phase relatively early in their life, where you see this luminosity versus age. There's this plateau that's occurring for objects bigger than 13 Jupiter masses during this brief deuterium burning phase, which then goes away. So it's not really an important part of their long-term lifetime, but okay, they have this phase of nuclear burning, so that's as good a dividing line as any. And now there are, of course, some issues with that, is that 13 Jupiter masses is not a universal constant. What this value is for the onset of deuterium burning depends on various factors, one of which that's demonstrated here is what the metallicity of the object is. So metallicity dependent value. But okay, well, so some people like that as a distinction. Others say, well, so maybe a little arbitrary. Some people like to argue that, formation mechanism is what counts. We think we understand something about how stars form, whether in isolation or in multiples, as many stars form. But that there's something different about how planets form, in particular, this presence of this heavy element core that many of them have. And so we should try and classify things based on how we think they formed. Of course, there's problems with that, because you observe an object, you just know it's there. You don't know its whole history and how it's formed. And for extrasolar objects, it's hard to know, is there a heavy element core in there or not, depending on the precision of mass radius measurements to know the mean density and things like that. So I think what I think, and I'm not, I think, alone in this, is that, well, all these things are sort of fuzzy. And as scientists, maybe the best thing we can do is go with sort of probabilistic classifications based on population statistics. And what do we think, what do we think things look like based on their observed properties, and how they correlate with things like metallicity and whatnot. And for a given object that's at the boundary, it may be impossible to say exactly how it formed or whatnot. And we just have to live with live with that uncertainty, that we have overlapping populations that might form in different ways. Thoughts on any of that? Yeah.
I guess the first question is, for a given object, why is it interesting to know it's more of a giant planet or more of a dwarf?
Yeah. So, well, there's there's sort of cynical and less cynical answers to that, I guess. But the less cynical answer is that, well, we do care about all these issues of how they form and how they got to be. And so, yes, if we, see an object that is, 15 Jupiter masses out in a disk, we want to know, oh, wait, is that something more like a binary companion, or is it more like a giant planet in our solar system? So it's just understanding the nature and origin of these objects. Yeah.
Found the more non-cynical
Yes.
way to look at it. I was thinking, so if how long does this deuterium burning last? Like, do they have, like, we cannot distinguish between, well, let's imagine, but could we distinguish them because of some other effect that they're having in their environment, or kind of what little things will make them different to say, like, oh, I have a 13 Jupiter mass planet, or is it a brown dwarf? How can you distinguish between both?
Yeah. So, I mean, as for the answer of time scale, you can sort of see that here, that I guess the time scale when you're, I guess, near the boundary, I guess, burns at a slow rate and it extends a little bit longer. It seems out to about, 100 million years or so. So yeah, I mean, so this is certainly important for direct imaging surveys, right? Where in general, whether you're deuterium burning or not, you want to, right, try to catch these objects when they're young, and that's when they're most detectable. But obviously, if you're, observing at ages of 10 million years or so, right, this sort of, right, the brightness dependence on mass becomes very steep in that range. And so there's going to be a bias towards finding objects which are above the deuterium burning limit if you're, trying to find these things when they're bright and young. And so that's why, but obviously sensitivity is getting down. So we now have direct imaging of objects, which seem to be clearly below the deuterium burning limit.
This deuterium burning limit, you said, depends on your metallicity. Does it also depend on the distance to the star? For example, if there's more tidal forces and that kind of thing.
Oh, I'm unaware of any work on it. So I've actually done some work on sort of hot Jupiters, and certainly these cooling tracks that you see are significantly affected by irradiation, right? So yeah, how that then couples all the way to the interior is maybe a little a little harder to say. Well, I guess I could speculate that if you have an inflated object, its central pressure is going to be a bit less, so it might be a little harder to ignite the deuterium. So that's my hypothesis. I don't know if there's papers on that. All right, we got another project here: deuterium burning in highly irradiated brown dwarf companions. I don't know, Phil, you've done all this? No. One of the experts on hot Jupiters and many other things. All right, so yeah, another fun thing I thought I'd share. Obviously, there's lots of exciting JWST results coming out all the time. I mean, one of the ways we can try and distinguish between obviously the planetary and stellar populations is understand what the stellar IMF is really well. There's of course this for higher mass stars. There's this famous salpeter IMF of the NDM going as m to the minus 2.35 or so. This distribution obviously can't continue forever. It would blow up at low masses, but that's fine. We know the IMF turns over to low masses and to brown dwarfs to this slope that is less than 1, and so it does not diverge. But it's still pretty flat. And so there is this recent paper that I noticed, which is saying, okay, let's not just fit all the brown dwarfs with a single slope, but let's try and fit it with 2 slopes and a break and try and figure out if there's a break, where it is, and what happens after that. And when they do this, obviously, the statistics aren't great. This is, still very hard work, but they are able to go deeper and deeper with JWST. And so the claim is that, okay, yes, for higher mass objects above you know, 10 or, you know, some errors here, 10 or 20 Jupiter masses or so. You have this standard brown dwarf IMF, but then it really steepens and drops off below that. And so these lower mass objects are really, really rare. And so that's, you know, obviously you have to be very careful about your completeness and saying there's a drop off in very hard to detect objects, but that's what they claim to have done. And to have found that, yes, the free floating planets are rare, but there are some of them.
Sure.
Yeah.
How are they getting masses for some of these lower mass brown dwarfs?
Yeah. So these are obviously based on based on the brightness and some sort of cooling effect. So they're looking, I don't remember the details of where they looked in some young cluster where they presumably know the age and that. This is okay. So as for planets, of course, there's ideas going way back to various philosophers that, you know, we know the planets in the solar system are orbiting in the ecliptic, and so that they originated in a disk. And I think it's been one of the great advances of science that we now observe those disks and study them very well. And this hypothesis seems very, very secure. But how does that actually happen? Well, there's sort of a leading hypothesis that really explains the diversity of planetary systems, not just the giant planets, but also the terrestrial planets and all the debris we see in debris disks. And that's the core accretion hypothesis. And so that, roughly speaking, can be broken into several stages. There's going from the small dust grains that everyone in this workshop loves, up to planetesimals. I've talked about that some in my lectures, so I'll maybe say a little bit less about that in the interest of time. And then once you form, you know, 10 to 100 kilometer scale planetesimals, those need to grow further. And those can grow by giant impacts or also by accreting more dust and pebbles. And then if that core gets big enough and its gravity, right, the gravitational energy becomes strong compared to the thermal energy of the gas, it can start attracting not just a thin gas atmosphere, but wrong term there, a significant gas envelope, a lot of mass. And then one of the complexities of this whole process is that as these planets are growing, they're exerting strong torques on the disk. This causes gaps to open at some point. It can also cause the planets to migrate. And yes, and then the planets can also scatter off each other. Did I see a hand? Or... Very general picture. So we'll try and get into some of the details of these steps. All right. But of course, the core accretion idea is not the only way to make a companion in a disk. The other way to make a companion in the disk is a simple, in some ways, a simpler one-step process. It's that if you have a disk which is gravitationally unstable, and which is massive and gravitationally unstable, the gravitational fluctuations, right, if they get over dense enough, they can lead to the formation of fragments, right? And so this is something we talked about in the lectures, where the criterion for when a gravitationally unstable disk can actually produce fragments, it requires that these fragments cool on a time scale that's comparable to a single orbit in the disk. And that work on cooling times suggests that fragmentation is, in general, only something that can occur with, you know, realistic opacities in the outer regions of disks beyond 50 AU or so. And yeah, so. All right. So just to sort of summarize these some of these the two yeah.
Can you get so you said mostly fragmentation mostly happen in the outer disk. Could you get the disk which is doing spirals in the inner part and fragments in the outer part?
Certainly, yeah. So if right, so I think yeah, the point to make is that gravitational instability can have different outcomes. Obviously, fragmentation is one of those outcomes. Spiral arms, which drive angular momentum transport, is another. There's also a discussion of whether, in addition to ordered spiral arms, can you get a more disordered graviton turbulence from gravitational instability? And there's sort of ongoing work on that. That maybe shows up more in local box simulations and is harder to see. And when you're in a global scenario, you do more often get the spiral arms.
But same disk can show several times.
Yeah. Now there's several issues. There's also the issue of where is a disk gravitationally unstable. So in addition to the cooling being fast, in addition to the cooling criteria being met in the outer disk, it's also true that disk self-gravity often tends to be strongest in the outer disk. This is usually measured by the Toomre Q parameter. And so when this is plotted in in most disk models, Q is not some uniform value throughout the disk. It often has some local minimum somewhere, usually towards the outer regions, because the disk is cooling and because of how the mass is distributed. So it's an interesting thing with, some instabilities like convection. It leads to, oh, nice uniform entropy everywhere. Gravitational instability does not seem to do that. Even when it's active in a disk, it doesn't make things uniformly gravitationally unstable everywhere. It is more uneven and sort of complicated than that. So
just like following on that. So I feel like observationally, we don't see too many gravitationally unstable disks. I mean, there are some, AB or Riga or Alliance 27, but not so many. Like even in Axolma, which are like the most massive disks, I think they're still gravitationally stable. So do you think it's like a time scale thing that this process lasts for too short, and that's why we don't really catch disks when they're gravitationally unstable? Or do you think it's just because they're not gravitationally unstable?
Yeah. No, I think that's right. I think, time scale is a lot of it. I think, often people discuss the intense gravitational instability is probably going on during, sort of class 0, class 1 embedded phases. That also makes it harder to observe and can be briefer. And of course, right, accretion is also very episodic. So it might happen in phases. And so that obviously involves, in many cases, the cooperation of gravitational instability with some other transport mechanism to get these sort of limit cycles that give you things like FU Orioni outbursts that are, only happening during brief periods. I don't know if any of the observers who study this want to comment on their efforts to find more gravitationally unstable disks.
There will be a third one. Yeah, there will be a third one based on spiral motion.
Right.
But still, I guess.
Great. Yeah, I'm sure there's many more than 3 in the universe, but it's great that we're finding a third. Great. So again, in these sort of 2 hypotheses, so core accretion, it's again this sort of nice unified theory. You explain everything from planetesimals all the way up to giant planets. It's got this excellent feature that seems to work well with the observations that, it explains why giant planets are enhanced in metals and also tend to exist around more metal-rich stars. It's a process that, in principle, can work over a wide range of disk radii. You don't have to form your planets at 100 AU and migrate them into 0.05 AU if you have hot Jupiters. And if there's an issue with the theory, it's this multi-step process of things getting together. So there are timescale concerns. You have to do a lot within a million or several million year lifetime of the disk, because you have to, you obviously have to do it all while you have a significantly massive gas disk. You can't just, terrestrial planet formation in principle, you could wait and do that over tens, hundreds of millions of years, because you don't need to create a lot of gas, but giant planet formation needs to be fast. And for the idea of gas disk fragmentation, well, this is really the question. Okay, we really think this is a process that's quite effective at making stellar and brown dwarf companions. And the question is, well, what is the low mass tail of that? And what do you get out of that low mass tail? And so it really seems most effective at making companions which are more massive than 10 Jupiter masses on wide orbits, as we said, outside 50 AU or so. Although, of course, this mass should really be thought of as more of a mass ratio. And maybe this is the value around solar mass objects. When you're talking about companions to, say, brown dwarfs, then the mass ratio is something you should look at, and then forming lower mass objects does seem possible. And of course, you're doing this in a massive disk, so there is the possibility that these objects will migrate into closer distances. They don't have to stay where they form. There's some thoughts that you can form a really massive object, and then if it then collapses slowly enough, somehow you can rip a bunch of that gas from it, and so you can wind up forming a low mass planet from the gravitational instability mechanism. Those seem a bit finely tuned to me, and some people who've looked at this process in detail agree that it doesn't seem to be that effective. So, and I should say, in addition to the massive disk causing greater migration, I forget if I have this in some other slides as well, often people will quote a mass that's the initial fragment mass that you measure in a simulation in a few orbits. The fact that this planet is in a very massive gravitationally unstable disk, it is very unlikely to stay at that initial mass. So there's, it's an important thing.
The reason that the disk fragments more easily on the outer part is cooling, and on inner parts because the heating from the protostar is heating the inner part of the disk, or why?
And the inner is just so optically thick that makes the cooling time very long. It's just hard to compress it. That heat just can't escape from these fragments. So it's really getting up again. And yeah, in a way, it's sort of why, yeah. And obviously, because these disks are massive, they're probably even more optically thick. That can make it.
So Andrew, about 5 or 10 minutes left, and then I know there's a lot of questions already, but then we'll turn to open discussion. So just want
to. Sure. All right. So let's see. I don't know what we want to share. So I'll just sort of highlight some of the things I have slides on, and then we can choose which of those we want to talk about. So I've got a few slides here talking about what I think is sort of the observational evidence that seems to favor the core accretion hypothesis as the process that makes most of the giant planets. And that's related to this metallicity issue of the host stars I already mentioned, as well as the orbital distributions. So we could talk about that some. So we've got some slides on that. Then, if we want to have a little bit more of a theoretical discussion, we could discuss sort of what the basic scales of the problem are in planet formation. And here, right, there are various scales. There's a Bondi radius that's the condition for trapping an atmosphere. There's a Hill radius, which is the radius for being gravitationally bound and response to the tidal shear from the star. This is also where satellites to a planet need to be inside this Hill radius. And then, of course, we're doing this in a disk. So there's another important length scale that is the disk vertical scale height. We talked about some in the lectures. And obviously, the gas density is going to be constant within that scale height, but then drop off outside it, as you see there. And in understanding these length scales and how they relate to each other, it's very important to the sort of most important mass scale in this problem is what most of us call the thermal mass scale. And so this is a factor of the disk aspect ratio, h/r³ times the mass of the star. And basically, whether your planet is above or below this thermal mass controls the strength of its interactions with the disk, which you can actually see as the ordering of these length scales. So the way I've drawn this here, where the Bondi radius is the smallest, and the disk scale height is the largest, is what happens when your planet mass is less than a thermal mass. So you see, in that case, you can think of the gas disk as just kind of this infinite uniform medium, and the planet is not perturbing it greatly. But then when you get to, all right, well, when you're at the thermal mass, all these length scales are basically the same. That's what's so special about the thermal mass. And then when you're above the thermal mass, now you see the planet has a gravitational influence, which is even larger than the scale of the disk. It's having very strong gravitational interactions with the disk, and the full 3D geometry of the problem really needs to be considered in full. And of course, this thermal mass is also very important for the torques that the planet is exerting on the disk, how it opens gaps, all of these processes. And so just to understand what the value of that is, it obviously depends on, this is another reason why understanding temperatures in disks matter, because this is proportional to temperature to the 3/2 power. But if you have a sort of fairly cool, sort of passive flared irradiated disk, the model we talked a lot about in the lectures, you get that this is around the mass of sort of an ice giantish type planet at 10 AU, but scaling with different distances. There are people who think, oh, the thermal mass is about a Jupiter mass. Well, if you go far enough out, or if you make the disk thicker, that can be true, but it also can be much lower than that. Yes, and that very important for all those reasons we said. All right. Let's see. This is a slide where sort of, if we wanted to talk more about what the mass of the fragments in a gravitationally unstable disk are, there's been lots of work on that, as well as some including some recent progress. I'll sort of leave that as something we can get back to if we want. And we already talked about planetesimal formation in our lectures, so that's the idea of climbing up the size ladder of small grains to large grains. As the aerodynamic coupling, these dust grains start to decouple from the gas as they grow in size as well. That's something we measure with the stopping time, and then that allows different processes to take hold, from coagulation to vertical sedimentation, and then gravitational instability, possibly mediated by the streaming instability or concentration in dust pressure bumps. About this as well in the lectures, what these rings actually are, great chicken and egg hypothesis of are the planets there already? And maybe the thing I'll finish on before we open it up to more open-ended discussion of what we want to talk about, is because this is another area where there's been significant progress on in recent years, is understanding, once you form planetesimals, how do you continue to grow that protoplanet that might become the core of a gas giant? And so, as we said, there's a couple options. The sort of standard picture is that, turn everything into, planetesimals bigger than a kilometer, and then it just is basically an n-body problem of getting those planetesimals together. An n-body problem because the effective gas drag on large bodies is relatively weak. But there's been a lot of recent work on this idea that, you can also, there's lots of smaller debris left over even after planetesimal formation. And these smaller objects, often called pebbles, are still aerodynamically coupled to the gas. So by pebbles, people actually mean this, well, as I said in the lectures, but didn't say in this talk, that ratio of particle aerodynamic stopping time to orbital time, often called Stokes number, having that number be 1 or 0.1, closest to 1, so that the particles are strongly coupled, but not too strongly coupled. And here we can see sort of what the effect of that is. So these are trajectories of particles of different sizes and different aerodynamic couplings in a review chapter here by Anders Johansson and Michiel Lambrechts, sort of building on the original theory developed by Chris Hormel and Hubert. And so we see here in the blue curves this is effectively a large planetesimal. This has a very large Stokes number, long stopping time. And so what happens with these objects, if their velocities, random velocities, eccentricities, you want to say, are low enough, they come in on these orbits that are nearly circular. They get gravitationally focused towards the planet, but then when they enter the Hill sphere, well, things kind of go a bit crazy, right? And you are actually much more likely to scatter the object, right? The orbit is essentially random in here. So your probability of collision is essentially the ratio of the size of the planet to the size of this Hill sphere, which is a very small fraction. So in growing in this standard n-body way, one of the things, well, I think Peter Goldreich and maybe others said is that planets like to heat their food before they eat it. Scattering, throwing it around, eventually wind up accreting it. So in these other curves, you're seeing here the effect of Stokes numbers of, I believe, 1 and 0.1 respectively. And so here what you see is that, well, when particles enter the Hill sphere, because of their coupling to the gas, right, they aren't dramatically scattered, but they're sort of aerodynamically guided towards the surface, and a very significant fraction of all the objects that enter the Hill sphere are actually accreted, and only a few of them maybe get deflected or pass through because they're tied to the gas. So for this aerodynamic pebble accretion process, there's a lot of advantages. The accretion rate can, in principle, be a lot larger. And also, it's a process that's not limited to the so-called feeding zone of the planet, right? If you have a n-body distribution of planets, you accrete all the planetesimals in your vicinity, it's, going to take a long time, essentially forever, for other planetesimals to get into, right, come close enough that you can accrete them. Whereas with pebbles, we know they radially drift through disks, so you can just continually get a supply of new material to eat, as long as there's nothing further out in the disk that is trapping the pebbles and stopping them from getting to you. So this has been a big development because it really eases a lot of the, as we said, the main issue with core accretion is, can it operate quickly enough? So this gives a way for what might be the rate limiting step of building the core, of having that occur more quickly. It's, some will tell you that this cures all the problems in planet formation. But there are maybe a few caveats to at least consider, and that people are indeed working on. And again, this is a little semantic. This is a process where the accretion rate can be fast, but especially when it's fast, it's a very inefficient process. So everything that's entering the Hill sphere is maybe getting accreted, but when these Stokes number 1 particles are drifting quickly, right, this orbit extends all the way around the star. There's a lot of dust grains that are just passing by and don't get accreted at all. So there's a significant supply of pebbles flowing through the disk. The rate of pebble supply in many pebble accretion models is of order 100 Earth masses per mega year. That's a lot of pebbles, right? And so that's what you need to, and in some cases, to juice up these rates to be really large. There's another more subtle issue, which is interesting, maybe sadly more interesting in light of recent budget proposals. And so that's that this is a growth process that is so-called oligarchic. So what does oligarchic growth mean? So if you look at the growth time scale of a planet, its mass divided by its accretion rate, right? The growth time scale is such that it's not that the most massive object runs away and accretes all the mass, but the masses tend to equalize and you have large numbers of equal mass bodies. So that means even in this pebble accretion scenario, there's likely needed a phase of mergers of other massive bodies. It doesn't. isn't completely. And so indeed, and in modern models, that's indeed what's done, that people are combining pebble accretion with the end body dynamics of the growing planets. And that's what happens. So there is, of course, more to say about gas accretion, but I guess I think we did hear a bit from Leo about that already, and at least those of us in the workshop, about the great work he's done on the hydrodynamics of gas accretion. There is an earlier stage where the gas accretion is more in a hydrostatic phase, and the atmosphere is matched onto the disk. And this is a Kelvin-Helmholtz cooling process, which may indeed be the rate limiting step. And some of us at Arizona, including our current postdoc in our group, Avery Bailey, is working on this issue. So
Great. I
yeah.
think we probably conclude now, and then we can have a discussion. Yeah. So is that your last slide there, Andrew? So I think you stopped. So let's thank Andrew then. So thanks, Andrew.
Okay. Oh, they did that here.
Okay, no, we couldn't hear you. Anyway, so great. Thanks again for a great overview. So let's now have a discussion. So Ryan at Virginia and Joe at Chalmers, please help me moderate from each of your sides there. So Andrew, you summarized, I think, in principle, 3 different formation mechanisms if we include free-floating objects that can form a giant planet like you'd form a star. And there's some evidence from James Webb of the existence of these free-floating planets, although the counter argument is they can be ejected from a system. So that's, I think, still a little bit open what the lower limit is from the star formation point of view. And then, of course, you focused on the gravitational instability in disks versus core accretion, and where the core has to reach a critical mass and then has runaway gas growth. So let me first ask, my understanding is that because we see some giant planets in outer disks, that's always been claimed that we definitely need some formation via gravitational instability because the timescales are too long for standard core accretion. Is that still the current view? These directly imaged planets that are on very wide orbits at hundreds of AU, do they have to form by gravitational instability?
Yeah. So, is it okay if I sit while we have this discussion?
Yes, you can sit.
Okay, good.
You can show different slides, of course, now.
You told me I had to stand earlier, so I want to be clear.
Have a rest, yeah.
Yeah. So unfortunately, I don't think I have the slide that's been shown in most talks of the mass versus orbital distance distribution. I think everyone has seen that plot, and you've got the directly imaged companions, and they're up there in mass and out there in distance. And obviously that's partly because of observational sensitivity, but nonetheless, these objects exist. And so then the question is, well, aren't these the objects that gravitational instability should form? And I guess I'd say certainly for the more massive ones, that certainly seems obviously much more likely than it is for lower mass and closer in objects. So based on this sort of probabilistic view, I guess whether it has to be is obviously a bit harder to say. Right. Again, because the scattering is and orbital migration is possible. Now, I wouldn't want to lean on that too hard because these are very massive objects. So you generally think it's the lower mass object that gets thrown out. So then if that's the object that gets thrown out, what on earth do you have inside? So, but then, again, then I think, well, I guess I have didn't get through all my main slides, but I have my hidden slide. The system that people ask this question about most often is, and where I think it's maybe a bit most vexing because it's sort of challenging for both theories, is obviously the very famous HR 8799 system. And you see, I sort of bolded my overall view here is that, well, all distributions have extremes. And so, well, is this at the extreme of one end or the extreme of the other? I'd argue when you actually look at what these masses are, errors put them all comfortably below, 10 Jupiter masses, especially for the most distant object, forming something 6 Jupiter masses at 70 AU by gravitational instability, that seems very hard to me.
Well, that brings me to the next question, really. So,
Yeah.
I mean, what do we learn about the particular masses of these objects and also the multiplicity? So, has somebody simulated this system and can show it can form reasonably via gravitational instability in detail?
Oh, I mean, as you know, simulations of gravitational instability in disks are quite challenging, right? And yeah, so no, I would not. I'm not aware of a simulation of gravitational instability that can produce this.
Oh.
And my main argument is that even forming any one of these would likely be challenging based on our understanding of that process. That it would really be, pushing the limits and perhaps beyond of gravitational instability. While it's also, right, this is obviously on the extreme end of what core accretion, seems capable of doing with so many high mass planets.
But there are simulations of gravitational instability when they proceed and form planets. Do they form multiple systems typically, or would it be just a single object that tends to form?
Yeah. So, I mean, multiple fragments are certainly possible. Yeah. That's not unheard of.
Great. So then maybe we can come to the core accretion, and then of course we'll open it up in a moment because I'm sure there are lots of questions there. But from the core accretion point of view, is there a prediction or the kind of mass scale a planet should achieve? Because obviously, as you know, well, you mentioned the gas giants and the ice giants. Is the reason for the different masses expected with some interaction with the gas disk, or is it just the timescale which the gas disk is dissipating, or what sets these characteristic mass scales of planets? I suppose is the what is the latest in sort of how core accretion could predict say mass scales or demographics of planets?
Yeah. So, I mean, maybe we can, while we discuss that, maybe we can actually show some of these populations and what the masses actually are. So, what do we? I'm trying to think what the best one to show is here. So, yeah. So here, I think is a good example. This is the mass distribution of giant planets from radial velocity surveys. This one is from the Fulton et al. Work. And so and of course, radial velocities measure a minimum mass, m sine I, but we think that's sort of a smallish order unity correction. So here we have Jupiter masses, and so we see this distribution peaks sort of about, well, especially so these are minimum masses and the real masses pick up. This seems to peak around a Jupiter mass, and then okay, obviously larger errors at small masses, but then there's clear evidence for a fall off as you go to higher masses, and the 10 Jupiter mass objects are much less common than it's less common than 1 Jupiter mass. So this is one of the things you could say, well, this seems to be more a signature of core accretion, which would have the tail dropping off to lower masses, versus gravitational instability, which would have a population that grows to higher masses. I think that's pretty clear. But your question, Jonathan, was, I think, on the theoretical side of can core accretion actually predict that this is where the peak should be and how it should fall off. I'd say that's much more difficult. Obviously, there are population synthesis models that try and do this, but they do it largely by tuning knobs. And I think you identified what some of those knobs are. I mean, one is the overall disk lifetime. Obviously, the accretion of gas has to stop once the disk dissipates. There's this timescale constraint. But there's also the process where it's not thought that it has to be that finely tuned because of what we talked about, that as planets grow, they open a gap, and as that gap opens, the accretion rate drops. And so, but because that process is not universal, it does not predict an exact mass. There's still some accretion that goes on. So obviously how, the final mass is going to be, still depend overall on disk lifetime. And then, probably on other things like, how, how turbulent the disk is, and that's sort of, how effectively, material can accrete and sort of effectively viscously flow through gaps and all that.
Well, I have lots of other questions, but let's go to just check in with Joe at Chalmers. If there's a question there, Joe, let us know. Otherwise, I'm sure there are questions in Virginia. Joe, is there any question there? If not, we'll go to, so Ryan, please moderate some questions to Andrew if there are some.
Yeah, we have one question here from Ashish.
Yeah, that's a nice question. So, like, assuming like the most of the mass accreted is through pebble, can we see some observable depth in grain distribution in millimeter wavelengths or something? Like the wavelength corresponding to those pebble sizes. Do you think it's something which we can observe with like combining multi-wavelength data from ALMA PLA?
Oh, so yeah. So I'm curious what kind of signature you'd want to look for. I mean, I think the main question I would have, and I've heard others express this as well, is there actually enough pebble supply, right? And that's one of the things people have tried to look for is right? It's sort of a known thing that when people measure the dust masses of disks, right? Even the minimum mass disk model is maybe a bit above the median flux that's observed and interpreted as a mass. And so then the question is, well, is that just because you're observing at a late stage and most of the planet formation has happened already, which is, I think, a reasonable view. But yeah. So that's what I'm familiar with, is mostly just these basic mass budget arguments. But it sounds like you're maybe asking something a bit more detailed than that.
I was saying, like, for example, if most of the mass is accreted by pebbles, then those pebble size scales should be depleted in the disk, right? And you should see more smaller gains and more larger things, but not so much in the middle. So, like, can you see that depth if you combine like multi-wavelength data and you assume that the wavelength corresponds to the size scale, which still may disagree, and then maybe you see some depth in the distribution? I don't know. I know that's a random idea.
Yeah. No, it's great. I mean, I'm curious. Yeah, I think the concern there would be as well, at least in this picture, those large grains are drifting in anyway. And so they're going to be, whether they accrete onto the planet or just accrete further, either onto the star into optically thick regions, they would sort of be disappearing anyway. So I'm not sure that would be so distinctive.
Well, let me follow on from that. So can we tell the difference between pebble, how much does pebble accretion affect the composition of the gas giants? So can we tell from the composition now that's being measured, say, from James Webb transit spectroscopy of hot Jupiters, can we tell that they had to be enriched a lot by pebbles, or is it too complicated to model, or does the upper atmosphere reflect the bulk composition? Do you have any comment on what we can learn from compositional studies now of exoplanet atmospheres, gas giant atmospheres?
Yeah. I mean, all good questions. I mean, the general issue maybe some are aware of, right, is that, right, there are these ice lines in disk, and then the composition of these pebbles will depend on where they form. But then, of course, the pebbles will move and migrate through the disk. So that it's thought that, the original simple picture, obviously the most basic model, the famous Oberg et al., right? That there's likely a lot of dynamical effects that change that basic picture.
But even once you get to the planet, is the differentiation of settling of elements that it would be very difficult to infer the original composition, or can we assume they're well mixed?
Yeah. So I've looked at this a little, but not very recently. I think maybe Peter, I don't know, someone to speak a little more to what the current state of the art is for these C/O measurements.
Yeah. So I can speak on sort of what we're finding observationally. I think there seems to be more giant planets with substellar C/O ratios and elevated metallicity, so a few times solar. which seems to indicate some pollution by, I guess, O-rich things. But I'm not sure if that's pebbles or planetesimals or how that will work, and what disk folks predict will be the difference between creating planetesimals versus pebbles.
And that's mainly in hot
Yeah,
Jupiters, was it?
Yeah, these are mostly hot Jupiters. Yeah.
And we think what about this issue of settling? Does the upper atmosphere reflect can you infer metallicity of the planet?
Another thing you need to worry is that the planet is very hot, the accreting planet, and those pebbles will be vaporized once it enter, and some of the gas might be recycled with this new and Bristol-Mel's work. So really need to take care of all of those to compare with the existing exoplanet atmosphere.
Yeah. I mean, I think maybe I can just sort of. I didn't like what I was doing with my slides there. Yeah, I just want to, that's a great point about recycling. So just wanted to share that. But yeah, exactly, that there is this sort of significant stage right before runaway growth when the core can still be growing and doing pebble accretion, but there's a gas envelope on there. But even though the envelope is somewhat continuous with the disk, it's now known that there are hydrodynamic flows going on within this envelope. And this is, some people have used it to say, well, you can't make giant planets at all, because for the key point of this process is that for the envelope to grow in mass, it needs to cool, right? And if you are continually introducing fresh high entropy gas from the disk deep in this envelope, that will be keeping it hot and not allowing it to cool. And so the name of the game, as you can see, is to try and construct models. This is a cartoon, but based on simulations that Avery has done to say, oh yes, well, there is some recycling, but you're still getting cooling. And so, the cooling rate is maybe not as fast as it would be without recycling, but there is still some cooling. And now, so that's just for the growth of the envelope. And as you're saying, there's then also issues for what this does in terms of the delivery of the pebbles and their composition into the planet, because it has to get through this envelope to eventually either join the core or just be part of the stay part of the envelope for a long time.
We're close to the top of the hour. We're actually at the top of the hour, but I have one burning question I have to ask, if that's okay. So when you have the super Earth systems, the close-in super Earths, the statistics of whether you have a giant planet in the beyond them or not, can you comment a little bit? I know there's been some debate in the last year or two about whether it's more or less likely to have a giant planet around the system.
I not looked at this lately. I know I've definitely done this when I've done some teaching. Yes, I mean, I believe, yes, there is right. There are a significant fraction that do have outer giant planet companions. I don't know if anyone remembers more specifically what those statistics are.
There was a recent paper about super Saturns and Jupiter-mass planets. But as I was reading, I do not trust the statistics are like. How do you know there is no more planets behind?
I think the debate is still somewhat uncertain. The effects they're talking about are marginally significant, should we say it like that? But there's definitely a lot of interest in the impact, of course, of if you have a giant planet there on the super Earths. I mean, do we even know? Do we know which form first? These kinds of questions.
Yeah. No, I mean, I think this is a case where you have to be very careful with your Bayesian statistics, because you have the super Earths are incredibly common and giant planets are intrinsically rare. So I think showing that they're more likely to exist in the super Earth population, right? That can still be true even if most of them do not have giant planets. So you just have to, I think, yes, obviously some of this is how you define your question.
Okay, any last burning question for Andrew?
It's the same conversation question, but for gravitational instability. So my understanding is that Jupiter, Saturn are very higher listed than the Sun. Can you get that through gravitational instability to select them?
Well, so I think most people would say no, because gravitational instability occurs in a young, early phase. Probably the composition is, matching the composition of still the ISM material. I mean, right? A lot of people model a gravitationally unstable disk in isolation. That is not how it occurs. For a disk to be driven to gravitational instability, it likely still needs to be actively receiving infall from the molecular cloud. So that when people want to explain solar system planets with gravitational instability, they argue for this sort of tidal stripping mechanism. And so this really gets into how finely tuned that is, that you have to, right, well, you've got to segregate the solids, but then not actually collapse so much that you can still tidally rip off a significant amount of your gas envelope. So that would be the model that would try to explain that. But
Very good then. We should close up here. So let's thank Andrew again for a great talk and discussion.